In this video, we are going to go through the derivation for the rate constant for a first order kinetic. Now, what is the rate constant for a first order? It is basically written this way. That will be K1, and that is equal to 1 over T ln A divided by A minus X. So how can we actually derive this stuff? Now, bear in mind, we could also write this way. We could also write it as 2.303 divided by T, and you have log to the base 10. This is A, and this is A minus X. So how can we find these equations? How do we actually derive them? Now, if you have a reaction in which only one reactant proceeds to the product, this type of reaction can actually probably lead to a first order reaction. So you need to know that the reactant A in this case is actually having just 1 mole of itself. So if we wanted to write the rate law for this is basically going to be written this way. Now that will be negative dA dt, and that is going to be proportional to the concentration of the reactant A. That is how you write the rate law for a first order reaction. Now, we need to take this proportionality sign out, and that is going to create something like this. So this will be equal to, and we will have K, and that is going to be A. Now you could also write 1 on top because actually we just have 1 mole of the reactant A present there. Now, it's also possible for you to write, instead of writing square brackets with A enclosed in it, you could also write stuff this way. So this could also be written as minus dA dt, and this will be equal to Ka. You could also write it this way. Now, A, which is the same thing as the capital A in square brackets, that is the initial concentration of the reactant. So this will basically be the initial concentration. So what is going to be the remaining concentration after some time? So let us just designate the final concentration as A minus X. Now this X represents some value that would actually get deducted away from the initial concentration after some reaction actually begins. Now, if I have A to be the initial concentration, then I could write this one in a more specific term. That will be A naught. So if this is A naught, I could now write another form of the remaining concentration as AF, which is going to be the final or the remaining concentration. So this is what we have. You just need to bear that at the back because we are actually going to use it in the process of the derivation. Now, what you need to know is that this is actually the rate law for this reaction at time t equal to 0. That is actually at the time when no reaction actually has begun in this chemical process. So if you have that the time for this reaction is actually equal to 0, then you're actually going to have the rate law to be written this way. That will be minus dA dt, and that is going to be equal to Ka. That is how to write it. How about if some amount of time has been exhausted? So what you need to know is that after some time t, some amount of the initial concentration would actually get deducted or decreased away from that reactant and would actually cause products to be formed on the right hand side. So let's say after some amount of time t. Now t will be some value which we might not actually be able to tell, except we actually measure the conditions of the reaction. So in this case, we're just going to designate that as t. Now, if that happens, the amount A that you see here would not actually be the amount remaining. some value x or some amount x would obviously have left the initial concentration. So you are actually going to have something this way. Instead of we having A proceeding to the products, we're actually going to have A minus X, which will proceed to the product. So this is actually what you're going to have. And this is reasonable because some amount X has left A, and that will cause products to be formed on the other side. Now, if we have this, how can we write the rate law for this process? And this will basically be written this way. I think I need to wipe out some stuff away from here. So that is going to be after some time t. So that is going to be negative d, and you're going to have a minus x dt. And this will be equal to k. So that should be k multiplied by a minus x. Now remember, in the beginning, we had this one. That is the rate law equation for a reaction in which you have no time being spent. But this is after some time t. So I think I need to rewrite this stuff on top at this place. So this is after some time t. So you need to know that after some time t, the amount that was present there would no longer be a. It would now be a minus x. So the rate law would correspond to this stuff that you see here. So I can now wipe this stuff out. So we have negative d, and this is a minus x over dt, and this is into a minus x. And the next thing I'm going to do is I'm going to take dt and multiply with k. So this is going to be k dt multiplied by a minus x. And the next thing I will do is to take a minus x and bring it to this other side. This is actually reasonable to some extent. So let us have that. So this is going to be minus d, you have a minus x, and this will be divided by a minus x. So I'm just going to write that there, and we're going to have a k dt here. Okay, so I'm actually going to split this stuff and write it this way. So we're going to have a minus d into a minus x, and that will be divided by a minus x. So while we are differentiating this stuff, we're not actually differentiating this. So this would actually be like a constant. If you don't want to do it that way, you could just take dt and bring it back here. So that is basically going to be divided by dt. If you did that, then there should actually be 9 on this side. So that means you divided both sides and brought this stuff to this side. And so this will be k generally. So you need to know that this could actually be split or expanded such that if you have negative d multiplying into this bracket, you could have a minus dA and minus d multiplied by this. That is going to give you a positive dx. So that will be dt. And then we have 1 over a minus x. And this is equal to k. Right? So let me split this stuff. Now this could be rewritten this way. This is minus dA and over dt, and that will be plus dx divided by dt. So this is multiplied by 1 over a minus x. And so this is equal to k. Now, the next thing I need to do here is to wipe out this stuff, because I know that A is the initial concentration. A is actually going to be a constant, because that is the concentration for the reactant in a situation where T was equal to 0. So as far as time is not changing, the quantity that is attached to that stuff will be a constant because time is not changing. And so A becomes a constant. So as you can see in this place, what that insinuates is that we have the derivative of a constant with respect to t. So that will be 0 because if you differentiate a constant, that should give you 0. So basically, we're just going to have dx. Now, x in this case is a real variable because we do not know what it is. But we know that it is some value that was deducted from the initial concentration. But we don't actually know its specific value. So this will stand. But this one will cancel out. So what we should have here is dx divided by dt, and this is multiplied by 1 divided by a minus x, and this is equal to k. So now we are actually right on track. Now I'm going to take dt and bring it to the other side as I cross multiply, and so I'm just going to leave a minus x as a denominator in the left hand side. So this is going to be dx divided by a minus x, and this will be equal to k dt, right? Now, the next thing that I need to do is to integrate both sides of this equation at upper and lower limits. So what is going to be the upper limit of the left hand side? So that is basically going to be the variable. So that will be at x equal to x and x equal to 0. For this one, that is going to be t equal to t and t equal to 0. So this is going to be x equal to x, and where x is equal to 0. So this will be, I could just write it as 1 divided by a minus x. Well, so this is multiplied by dx. And on this side, I have integral t equal to t, and t is equal to 0. So we're going to have a k dt here. Now, k can come out as far as it is a constant. So we're not actually going to deal with this one, because if you have a constant multiplied with a variable, that constant can actually be pushed out. So this should be x. So this is going to be 1 over a minus x dx. And on this side, we're actually going to have k multiplied by integral. So this will be t equal to t and t equal to 0. Then we have a dt here. So we need to integrate this one. Now, if I had integral 1 over u dx, what I basically need to do is to take the u and operate with the natural logarithm of it, and that will be divided by the derivative of u. So that is going to be written as u prime. So let us work it out. So let's take u in this case to be a minus x. So that is going to be a minus x. Now u prime will be the derivative of this stuff. Now the derivative of a, which is a constant, should obviously be 0. Now the derivative of negative x should give us a negative 1, because we are actually differentiating this stuff with respect to x. So u prime should give us negative 1. That means if I actually wanted to do this, so that means I'm actually going to have something this way. This will be ln u. Now u in this case is a minus x. So this will be a minus x. And this will be divided by u prime. Now u prime is negative 1, so I just need to write it there. And so this occurs at the upper limit of x and the lower limit of 0. So this is equal to k multiplied by the other stuff which is here. Now if I integrated a derivative, that basically would cancel out. So I'm just going to have t and upper limit t and lower limit 0. So let us create some more space on top. Yeah. Cool. So this is what we have. Now, I just need to rewrite this. So this actually going to be changed into ln, and we have a minus x, and this is x, this is 0. This is going to be k into t. So we have t here, and we have 0 here. So what is the next thing that we need to do here? So we need to take the upper limit and substitute it as x in the first case, and subtract the answer by the substitution of 0, same thing as x. And we actually need to do the same thing for this other side. So this is basically what I mean. So I'm just going to use curly brackets to show this stuff. So this will be minus ln, and I have a minus, substituting x for x basically just remains the same thing. So this is what I have. Now I need to subtract this with the substitution of 0. So this is going to be minus ln again, and that will be a minus, in this case 0 will represent x, so that is going to be 0. So we have this. So that is what you're going to have on the left hand side, and on the right you have basically t, representing t in the first case, and that is subtracted by 0 representing t in the second case. That is basically how to work definite integrals. So this is going to be 0. Well, so I need to write curly bracket there. So this is what we have. Now how can we work these ones? It's pretty easy. We just need to take this stuff, and this is actually going to look this way. This will be negative ln a minus x, and this will be negative multiplied by negative, which should give you positive. So this is ln a, because a minus 0 is a. And this is equal to k multiplied by t. Now, I could rewrite this and make it look this way. This is equal to kt, right? Now, you need to know that if I had ln with another ln, and they're actually subtracting by themselves, then it's very possible to change this into a division. That is reasonable because ln is log to the base e, and so they actually have the same basis. So I could actually do that. So that is going to be log to the base e, and that will be a divided by a minus x. Or let me just make it straight up to look this way. And so this is going to be equal to kt. Now, log to the base e could be changed to be written this way. So this is ln a. Now we have divided by a minus x. And this is equal to kt. So let me just write kt this side. So this would actually look more forward in the direction that I wanted it to be. So I could take this to the other side, and that is basically by multiplying by 1 over t. So let me do that. So this is also 1 over t multiplied by ln, and this is a divided by a minus x. Now, this cancels this on the left hand, so we just have k here. And on this other side, you're going to have 1 over t. So this is ln, and you have a divided by a minus x. So this is basically how this stuff was derived. K is equal to 1 divided by t multiplied by the natural logarithm of a divided by a minus x. So you need to know what a minus x is. Let us start with a. A is the initial concentration, or I should just say the initial amount, because it might not always be just the concentration that will be considered in analysis. So a minus x is the final amount, or the remaining amount after some time t. Okay? So the time t would actually be told you. So after some time t, we have a minus x remaining. So this is how to solve it. But then there is also another form of it where you saw me writing k is equal to 2.303 divided by t, and this was multiplied by log to the base 10 of a divided by a minus x. So how did this come about? So let us see how that is done. So you need to know this law in logarithm. If I had log to the base a of b, and I wanted to introduce another base, that is going to be called the change of base. So this will be written this way. That is going to be log to the base c, and you have b, and that will be divided by the base in this case. So the base for the initial logarithm will become the denominator subject of the logarithm. So this is going to be log to the base of c of a. This is how to do it. So let me use that principle in this equation. So for this one, I have a k, and this is equal to now before I do that, let me just take t to this other side so that I'll reduce the complexity. So this is going to be t. This is equal to ln, and we have a divided by a minus x. So I want to change this. So we know that ln is a log to the base e. So this is a divided by a minus x. Now this is the base and this is the subject. So I could change the logarithm base. So let us say I want to introduce a log to the base 10. So that is going to be written as a log to the base 10 of a divided by a minus x. And I think I can wipe this stuff out. So this is going to be divided by log to the base 10 of this stuff, which is e. Now you need to know that e is approximately, well, is actually 2.72. So it's actually a constant. And so if we have log to the base 10 of e, that is ln e. Well, that should not be ln e. That should be it's basically log to the base 10 of e. So if you calculated it, it should give you some value. So let's go on. Need to wipe this one out. Okay. So this will be that k multiplied by t is equal to 1 divided by log to the base 10 of e, and this is multiplied by log to the base 10. So this is what we have. Now if you took this and plugged it into your calculator, this should basically give you 2.303. So we need to write that there. That means we have kt is equal to 2.303, and this is log to the base 10 of this stuff. So this is a over a minus x. Well, so I just need to rewrite this. Let me wipe this out. This is 2.303. This is log to the base 10 of a divided by a minus x. Now, in order to make k the subject, I'm just going to divide through by t. So that makes it to be k is equal to 2.303. That will be divided by t, and we will have log to the base 10, and that is a divided by a minus x. So we know that one way to write the rate constant of a first order is 1 over t ln, and you have a divided by a minus x. So this is one way to write this stuff, and this is another way that you could also write this stuff. So now you know how to derive it, and you know how they are actually transmutant of themselves.